Hello and welcome back to another lecture on the NPTEL course on advanced plasticity of solid continua. So, if you recall, we have been discussing about how to solve a nonlinear elasticity problem using the standard finite element method, right. A nonlinear elasticity problem, unlike a linear problem, has to be solved iteratively, right, and upon discretization we basically have a nonlinear algebraic equation which is solved by the Newton-Raphson like method in an iterative manner. Okay. So, let us now, having set the stage for what the algebraic equations are and how we arrive at the linearized form of that nonlinear algebraic equation into a locally linear form of an algebraic equation, something like k times delta u equal to minus r u, that sort of a thing. We are now ready to actually state the steps, that is, describe the iterative algorithm which inform the final solution in a computer. Okay. So, in step 1, so we are doing an iteration, consider the kth iteration, all right. So, until and unless the iterations are over, your solution is not obtained, and your iterations are stopped when the error with respect to certain norm between two successive steps, right, becomes a lower than or equal to some user specified tolerance. So, step 1, compute the strain as a vector. Remember that epsilon hat is the vector representation of strain, which is B times capital U. Recall that U is the vector of displacement degrees of freedom, all right. In step 2, you need to compute the stress sigma hat again as a vector by differentiating partially the strain energy psi with respect to epsilon hat, right, that is to compute the stress. Then your step 3 will be to compute the material tangent information, right, which is captured in C, right. So, that is equal to del square psi, the second order derivative of psi with respect to the vector representation of epsilon, that is epsilon hat, all right. So, that is your tangent material information. Then use this tangent material information, material tangent, to find the element base stiffness integral over element E, B transpose, B is the strain displacement matrix, C B d omega, correct. Assemble these element based information to find the global stiffness K. Through the dependence of C on the current iterative solution, which is, let us call it U, you see C is still a function of U. So, K is still a function of the last known U, all right. It is unlike a linear problem where K is a strict constant and you do not need iterations. Then find the right hand side minus RU. For that, find R as the assembled over elements of the element based internal force minus element based external force, right. So, the element based internal force is integral over the element omega E B transpose sigma hat d omega, okay. Then assemble them to get the overall residual R, right. It is still a function of the last iterative solution U, capital U. Okay. Then step 5, you need to solve the linear system K times the increment delta U equals minus R, right, and then update. So, K should be invertible. Why is K invertible? Because psi is a strictly convex function. For a strictly convex function, psi is a strictly convex function of epsilon. Strictly convex means it cannot be like this, right, this is not acceptable. It should at least be something like this, right. It should be smooth everywhere. I mean, there should be no points of non-smoothness. That means the second order derivative of psi with respect to epsilon can never go to 0. That means k is always, you can see that, right, except for the point where basically, so everywhere basically. So except even here, it is the highest, right. The unique point where the minimization actually happens, the curvature is the highest. So nowhere can it really go to strictly 0. So k is invertible because del square psi by del epsilon square is invertible. So therefore, we know we can actually uniquely solve for this delta u and update u as u plus delta u, right. So, so k is also called the consistent tangent stiffness, right, because it is obtained by exact linearization of the residual. All right, the exact linearization of the residual, there is no approximation anywhere except that we are solving the problem iteratively. So, okay, so we can only reach the final solution approximately, we can never really, we can approach the final solution, right, can never reach it perfectly. But the point is that because of this property of the Newton method, let me come to that, we have quadratic convergence. That means the rate at which we go to the final solution is quite high. In other words, the number of iterations we typically need is lower with respect to a pure gradient based method, all right. So these are very useful things. That is why finite element method converges quite fast even for nonlinear elasticity problems, right. Let us, because we have been talking of Newton's Hessian based method, that is the Newton-Raphson method, a quick recap will help you to understand it even better, right. So suppose we wish to find the minimizer of an energy like function, which is basically psi u for our case, right. So our objective is to find that u which minimizes psi u, that means arg min u over u of psi u, okay. So we must set the gradient of psi to actually 0 in the process, right. But let us, so basically that is the requirement. So gradient of psi is equal to 0 is my condition for optimality. Let u be the last available approximation as in our case, and delta u be the update, okay. Then what we do in Newton-Raphson, unlike a gradient based method, is approximate this delta psi itself by a Taylor series. We are not approximating psi, but we are approximating the gradient of psi itself by a Taylor series, right, just two term expansion. What is that? So gradient of psi, if I want to approximate about, okay, about the available u, okay, that will be the first term will be the gradient of psi itself, right, plus the Hessian, because the gradient of psi itself is the function which I am actually approximating. So this is the first term, right, correct, the usual first term, and the second term is, so basically this gradient of psi, right, times delta u plus the Hessian term, the delta u transpose del square psi by delta u times delta u plus small order of this is the remainder, right, Taylor's expansions remainder. The small order of norm of delta u square, what it says is that, what is this small order? The square, it means that it goes to 0 faster than delta u square itself. Delta u square goes to 0 quadratically, right, as delta u goes to 0, right, but this quantity goes to 0 faster than that, right, faster than quadratic. So that would mean that even after removal of this, the terms that are remaining must go to 0 quadratically, right. So that is the advantage. So, here if I call this term as h delta u, that is del square psi by this is the Hessian, which is symmetric and invertible for obvious reasons that we have described, that psi is a strictly convex function. Therefore, if you just remove the remainder, right, remove this term, okay, and set the rest of it to 0, then you have this. Okay, so delta u is the Hessian minus of Hessian inverse times this gradient of psi. Okay, this is exactly what we have been using to actually find the solution, in the last, in these 5 steps that we have just described. Okay. So, from the nature of the remainder, it follows that the order of convergence is quadratic, because the remainder goes to 0 faster than quadratic. So, this observe that this term, this delta gradient of psi is correspondent to the residual term Ru in our FEM based scheme. So, this is the Newton's method, a quick recap. Okay. Now, let us go back to viscoplasticity, all right, rate dependent viscoplasticity. Okay. And let us see how we can apply the same principle, except that instead our objective functional is only different. The rest of it is exactly the same, right. The objective functional is different, that is the only thing. So, what would be the objective functional? That is one of the issues now. Okay. And also remember another thing, that we now, irrespective of whether your problem, if there is an inertia term or not, okay, in elasticity, right, your problem may be time dependent or not. In nonlinear elasticity, it can be a static problem or a dynamic problem, but in plasticity, in this particular case we are talking of viscoplasticity, but in general in plasticity there is nothing called a static plasticity problem. Okay, it is a misnomer. So, plasticity always depends on the history. So, therefore, time discretization is a very important thing here, which we have not encountered in an elasticity problem, not necessarily, unless that the elasticity problem itself is a function of time through the dynamic forces and things like that. Okay. So, this time discrete minimization has 2 parts here. Okay. The functional that has to be minimized remains the same, but once we do a local update of that, what does it mean? That the functional is minimized given the available information on strain at time n plus 1. That means, suppose I have discretized my time axis, this is my t0, this is my t1 and so on. So, like this I have gone to tn, and my objective is knowing everything at tn, I have to go to the information to to be found at tn plus 1, right. So, epsilon n plus 1 is an available solution, because everything is by iteration. Earlier the iterations were being done irrespective of time, right, because I thought that okay, we were dealing with a static nonlinear elasticity problem, but here we are dealing with a time dependent nonlinear problem. So, therefore, over each such time interval we need to do iterations, converge and then go to the next interval, you understand. So, this is both a time recursion and an iteration over each time step. So, given the trial strain epsilon n plus 1 at my objective is to find everything here, okay, at Tn plus 1. So, given epsilon n plus 1 provided by some means we will come to, okay. So, given that information, find the internal variables. What are the internal variables? Like the plastic strain, then the hardening variables. These are the internal variables which actually describe the microstructural changes that are contingent upon the evolution of plastic flow. Okay. So, all these internal variables alpha that minimize this integrand locally. What does it mean by locally? Means we do not integrate the integrand over the entire volume of the body. We just do it at a point, a material point, right. These material points are typically selected as the Gauss points, because that is where the Gauss points you know how to integrate, right, by Gauss quadrature. If you do not know the method of Gauss quadrature, then my suggestion to you at this stage is to go back to an NPTEL course on finite element method or an appropriate textbook, a basic textbook, to cross check and recap or understand the Gauss quadrature method, right, for integration. We need integration later on for doing all these volume integrals that we have to do, right. So, here the update is entirely local. That means at each such material point, which are the Gauss points, we have to do this update of the internal variables, okay, through some minimization of a functional that I have not yet described. Now, I will describe that. So, the variational update, because it is the minimization problem of a functional. What is the functional? So, this is the functional actually, which contains the this strain energy. In this case, it is no more strain energy, it is basically the free energy, the Helmholtz free energy, right, because there is dissipation. So, we really cannot use the word strain energy here, and this is the dissipation potential, right. This is my functional in a discrete setup, but the actual functional in a continuous setup, in continuous time setup will be call it by j of alpha, right, correct, or basically j of alpha, yeah, okay, or alpha dot, it does not matter, okay. That is actually equal to psi plus psi dot plus phi. This is my functional. So, psi dot plus phi is the new functional, it is not psi. Earlier we actually minimized the strain energy, and that too globally, we integrated over the entire domain. Here in level 1 we need to do a local stuff. We have changed our functional, it is psi dot plus phi, the rate of change of the free energy plus the dissipation functional, which is basically a functional of alpha dot, okay. So, and psi dot is a function of strain, psi dot is a function of strain as well as alpha. Psi dot is basically a function of strain, okay, as well as alpha. Remember that phi is a function of alpha dot, not of alpha. Remember that, okay. So, you may question now, the question that arises is this the right functional? Is it the correct thing to really minimize? How do I know? That question you need to wait a little bit. I will come to that. Essentially this follows from a deeper principle in statistical mechanics, which is basically based on the work of Onsager and Maclap, but I will come to an explanation which is plausible for you at a later stage. For the time being, let us actually take this for granted that this is my functional, okay. Now, the discretized form of this functional is as something like this. So, what is psi dot? Psi dot is approximately, it is the derivative with respect to time, right. So, it is approximately equal to psi n plus 1 minus psi n by delta t, correct. Delta t is this time difference here, okay. This delta t is the time step. Now, this delta t, if you absorb here, you observe that psi n is a function of epsilon n and alpha n, correct. Psi n is basically a function of the last steps values, no, sorry, alpha n, correct. So, it is my objective is to find alpha n plus 1. So, if I differentiate psi n with respect to alpha n plus 1, it is 0. So, there is no psi n here, you understand. What we have written is the psi at n plus 1, Okay, the unknown is alpha. I need to find that alpha such that it minimizes the whole thing. So, therefore, this is alpha, right, and this delta t is absorbed here, the delta t which was here in psi dot, that is absorbed here, right. Phi is a function of alpha dot. So, we wrote it as alpha minus alpha n. Alpha n is already known, okay. This is known, right. So, alpha is the unknown. So, this alpha arises both here and here, correct. So, this is what I need to find. There is no integration, nothing. Now, do the stationarity, right. What is the stationarity requirement? Differentiate this quantity with respect to alpha and set it to 0. If there is any issue of non-smoothness anywhere, right, then the gradient of this appropriately has to be, this non-smoothness can be there in phi, as we have already seen, right, for some cases like the Tresca plasticity. If phi is smooth, which is easier to understand for the time being, then there is no issue. Otherwise, we have to use the sub-differential notion, but for the time being let us say that there is no such issue. So, therefore, this delta phi, which is the sub-differential, should be replaced by this gradient of with respect to alpha of phi. Okay. This is what basically it means, and this belongs to should be replaced by equal to. You understand? So, basically what we are saying that gradient of alpha is equal to minus del psi by del, the gradient minus of gradient of psi with respect to alpha. Okay. So, this is the condition, right. This is the condition for the gradient of the whole thing with respect to alpha, okay, to be 0. So, this is the requirement. This is the requirement for stationarity. So, this is what is in classical plasticity is called by the return mapping. Return mapping is a local information all the time, right. It is a local information on the update of stress. Okay. So, through the update of stress, it is also the update of the plastic strain, right. So, here we have a return mapping like thing, but done not through return mapping, but through a strictly variational update. Okay. It is a local update, remember that. That is the level 1, that is knowing epsilon n plus 1 how to find alpha, right. That is the first job. Level 2, once you have actually determined your alpha locally, then you are ready to do a global equilibrium at the structural level. That means find the displacements and hence the strain again. Okay. You started with some strain epsilon n plus 1, right. So, you have to update it now, okay, because alpha has been found. So, the local update is now solved. So, find first the stress, which is basically delta psi by delta epsilon n plus 1, right. This is the stress. Now, remember that the things become very complicated if we actually go on again distinguishing between vector and tensor. So, whenever actually finite element is involved, please understand that these quantities like the stress or strain has a vector representation through 6-dimensional vectors, right. So, I am not putting hats and all that again to complicate matters. What you have to understand is that wherever needed, it should be treated contextually either as a vector or a tensor as appropriate. Okay. So, therefore, our job is to find first sigma n plus 1 by differentiating psi with respect to epsilon. Okay. Now, the global functional, what is the global functional? The global functional is nothing but the integral of that j that we have already talked of, okay, minus your f external minus all these f external times the external work that we have already seen in the context of nonlinear elasticity through these two quantities, the the body force B and the traction boundary condition, right. So, the global functional is then minimized with respect to the nodal displacements un plus 1, all right. Nodal displacement, if you want to minimize this, if you call this global functional as delta pi, right, then this minimization will give you this residual r, which is equal to, which has to be set to 0, right. R is the residual vector. What is the expression? So, R essentially is now the current representation for the internal force, right, and the expression for this internal force is what? B transpose sigma, you remember, minus F external. So, this is exactly we have written here, okay. So, R is integral over omega, because this is a global update of these quantities, okay. So, this is the situation. This is still not completed, because we have still not linearized R, okay. R is still a nonlinear function of the nodal displacements. So, now we can actually come to the overall algorithm. In this overall algorithm, we will be linearizing R and solve a linear problem, linear algebraic problem, something like k times delta u equal to some force at every iteration over every time step, okay. So, the overall algorithm is as follows. I will not be able to complete this entire algorithm in this course, in this particular class, I am sorry, but we will go over again in the next class. So, let us start it, okay. So, in step 1, predict the trial elastic stress. So, sigma trial is the elasticity tensor times appropriately contracted with epsilon n plus 1 minus epsilon n p, the available solution for the plastic strain at time t n, okay. Now, this is the trial stress, assuming that there is no plastic flow that has occurred, okay. Sigma trial corresponds to a purely elastic step. The second thing, in step 2, we do the local update. That means we solve for the local update for the variational problem, that is to update the alpha. In this particular case, alpha could be just in the form of epsilon p, the plastic strain, right. So, we need to find delta alpha. If it is only a function of if it is only in the form of plastic strain, then you need to find delta gamma, which is norm of delta epsilon p, right. So, that is delta epsilon p is basically delta gamma times this f is basically the yield function, right. So, delta f by delta sigma, as you know already, at n plus 1 will give you the normal to the yield surface, okay. Because we already know that in Perzina model there is an yield surface, the concept of a yield surface is still there in the Perzina model of viscoplasticity, okay. So, this is my delta epsilon p. So, towards this, in step 2, that is to solve for delta alpha, we need to solve this following minimization problem. Remember that now this alpha is nothing but delta epsilon p. We need to minimize this script j, which is nothing but psi at n plus 1 written in terms of this delta epsilon p plus delta t that factor coming here, right, phi of epsilon p dot, that is delta epsilon p by delta t. I did not write epsilon p dot because we are finding delta epsilon p. So, I have to write it in terms of delta epsilon p only, everything. Otherwise, how do I minimize with respect to delta epsilon p? Okay. So, for the Perzina model, this setting this to be equal to 0, that is the derivative of script j with respect to delta epsilon p equal to 0, leads to a single nonlinear scalar equation for this delta epsilon p, or in other words through this relationship for this consistency parameter delta gamma, which is the norm of delta epsilon p, okay, nonlinear algebraic equation in terms of a single scalar unknown. So, you can actually solve it again by Newton's or Newton-Raphson method, okay, that is at every Gauss point. That is the requirement, okay. Then comes your step 3, That is, we are now that we have found the plastic strain, at least an approximation to that, we need to update our displacement. That is our strain. And so to do that, in step 3, find the stress first. So stress is nothing but delta epsilon by delta epsilon n plus 1, correct. So from the last available delta epsilon n plus 1, I can actually determine this, right. It will still be a function of epsilon n plus 1, remember, because psi is basically a function of epsilon, right. Now it is at this stage that I need to find my stress, the displacement, and hence epsilon itself, right. So we need to actually do that global update, that is we need to integrate my functionals and minimize. In order to do that, we need to actually find the, again, material consistent tangents, okay, like C algorithm. So we will come to this issue of how to find the material tangent and the corresponding, the tangent matrix for the stiffness, right, and hence find the global update for the incremental displacement in the next class. What we have already set in motion is a process. As you can see, if you accept that this new script j, the functional, is indeed a valid functional like your strain energy in elasticity, nonlinear elasticity, to minimize, to find all your unknowns, except that you are now locally minimizing and globally minimizing, that is all. Then the method is exactly the same as you had with elasticity. There is no difference, both are strictly variational, and with this adaptation to a new functional to minimize, you have very little extra to learn about how to solve a problem in plasticity. That is one of the great advantages of convex analysis, and that is the reason why we have been following convex analysis in this course. So with this I will conclude this talk, and I will meet you again in another lecture shortly. Thank you for your patience.